Okay, can you see the slides? All right, good. Okay, last week we stopped here. So we discussed about the previous technology that was in the mass production that was called screen printed back surface field technology. And this technology still has a very small portion in the industry right now. And the current dominant technology in the mass production is called PERC, or passivated emitter rear cell. Okay, passivated emitter rear cell, and this is called PERC in short. So this technology was developed back in 1980 something. Okay, in UNSW lab, right? So it was first developed in UNSW, and then it was patented by UNSW as well by Professor Martin Green, and then licensed to different manufacturers to manufacture the solar cells. So now this technology, the PERC, is holding about at least 70% of the market share worldwide. Okay, so that means out of the 10 solar panels that you'll see on the roof or in solar farms or anywhere else, so about 7 out of 10 panel that you see will be based on PERC. So look at the device configuration again. As last time that we discussed, the solar cell is a PN junction device. So, so in this case, you can see that the PERC has a P-type wafer. So it uses P-type wafer. Okay. So then the PN junction is made by an N-type emitter, N plus emitter. Okay, the P-type usually has 1 times 16 carrier concentration or doping level per centimeter cube, and then the N plus usually has somewhere 3 to 5 E19, say about 3 E19. So these form a PN junction. Okay, so the PN junction is not the only structure in the solar cell. You need to have a couple more things. So you need to also have a thin layer of ARC, anti-reflective coating, which is based on silicon nitride, in this case, in the industry. So silicon nitride is used because it has an intermediate refractive index between air and crystalline silicon. So the air has a refractive index of 1, and crystalline silicon has an index of about 4. Okay, 4. And the refractive index is wavelength dependent, so it depends on the wavelength, but the value is somewhere 3.9 to 4. Okay, so we'll take that as 4. So when you have a very big difference between refractive index between material 1 and 2, so as you learned in optics last time, so you will have a very high level of reflection, okay, at the interface. So the interface is here between air to silicon, right? Air to silicon. So due to the high difference in refractive index, we're going to have a very high level of reflection. And this approaches 40% of the reflected light upon the incidence on the surface if you don't have any anti-reflective coating. Okay, so therefore, in order to reduce the light reflection, there are 2 strategies. Okay, there are 2 strategies being incorporated into the solar cell. Okay, 2 strategies in order to reduce light reflection. Right, the first one is to incorporate front pyramids here. You can see the pyramids. So you can see that the the front surface is not planar, right? It's not flat. Because if you have a flat surface, you're going to have a very high level of reflection, just like what we get on our mirror, okay? So in order to dress up, in order to see yourself. But it wouldn't work in solar cell because if you have a reflection of about 40%, that means 40% of the incident photons will be lost to the atmosphere and they will not be harvested in terms of electricity. So you don't want that to happen. So that's why we introduce the texture. This one we call it texture, the pyramid shape texture. Pyramid texture, strategy number 1, pyramid texture. So pyramid shape, and this is why we call it pyramid texture. So the texture or the surface is roughened with pyramids, right? We incorporate pyramids on top so that the light can be refracted and reflected into multiple angles, right? Upon the incidence, the light will be reflected into multiple angles. You can look at this on PVC drum as well. Okay, when the light strikes here, it won't be reflected off like that. It will be scattered into multiple directions. It will be refracted into. So this will enhance the probability of the light or the photons being coupled into the silicon solar cells for energy harvesting. Okay. So on the other hand, if you have a flat surface, so the incident light will just be reflected off about 40%. And this, in the second case, you can reduce the reflection to about 11%. Okay, so that is the first strategy in order to minimize light reflection, and that is not enough. So therefore, we need to have another layer that we call silicon nitride ARC, anti-reflective coating, that will further reduce the light reflection on the surface. Okay, so that's given by the blue color here. The blue layer here is a very thin one. That's about 75 nanometer of the ARC, and the refractive index of this layer is about 2.0. Okay, so then you have passivated emitter rear cells. So you have localized passivation as opposed to blanket passivation, as I explained last time. So we want to minimize the contact area between metal and the silicon. So in the previous technology that we call back surface field, we used to have contacts throughout the real surface between aluminum to silicon. You can see here the whole thing is aluminum contact, right? This is aluminum contact. So in the latest technology that we call PERC, the contact interface is only at these regions, right? So the areas of contact between metal to the semiconductor is minimized, and other areas are passivated with dielectric layers like aluminum oxide, ALOX, and silicon nitride, 2 layers there. So we use ALOX and silicon nitride. So this is the technology that we're currently using in the mass production. So if you look at Jinko, JA, Q-Cells, and in some other companies, they are based on PERC technology at the moment. Okay, so that's PERC. So since the last few years, Malaysia has been world number 3 in the PV manufacturing. So we are behind China and Taiwan. So we have a couple of Top Gun photovoltaics manufacturers in Malaysia. So that leads us to be the number 3 in the world right now. So if you look at these data up to 2018, so say if you look at 2018, then you can see China is number 1, China. So the second is Taiwan, and we are number 3. So we are the green here. Look at the green portion here, the increasing green portion since. Okay, you look at this from 2010. This is due to the presence of First Solar. First Solar is the first company that opened the mass production in Malaysia. And then over the years, we have more and more silicon companies coming in. So you can look at the green portion here, increasing over the years. And now we are world number 3 in terms of PV manufacturing. Okay, so there's plenty opportunities for you if you want to join solar companies. So we have a lot of companies in the northern region, in KL as well, in Malacca, in Kuching, right? So we have plenty of companies in Malaysia. So for example, if you talk about solar manufacturing, the first one is First Solar that was open about more than 10 years ago. I think, if I'm not mistaken, somewhere 2007, 2008, in Kulim High Tech Park. And then we also have JA Solar in Bayan Lepas, a couple of plants, and we have Jinko in Prai, a couple of plants as well. So now Jinko is expanding into Batu Kawan, right? They used to be in Prai, but Prai is already congested. So they're just building their latest plant in Batu Kawan, right? We have Panasonic Energy, although they just announced a withdrawal from PV industry. Panasonic Energy is in Kulim. We have Q Cells in Cyberjaya. Sun Edison, I think it's closed already. Sun Power in Melaka. Longi in Kuching, right? So all of these are doing crystalline silicon solar cell, the first generation, multi and mono, right? Multi and mono. First Solar is the only one working on cadmium telluride. So in Malaysia, we only have crystalline silicon and cadmium telluride. We don't have mass production for organic solar cells, not for ZAT386, and not for others as well. Just silicon and cadmium telluride at the moment. So this is the top 10 PV module manufacturers. So when I say module, it's referring to the panel, silicon panel. We also say module, right? Panel manufacturers. In last year, based on the volume of the shipment, how much have they shipped? Volume. So number 1 there is Longi in Kuching, and then we also have number 2 in Malaysia. Jinko is number 2. We have in Malaysia. JA we also have in Malaysia. In Penang, Trina we don't have it here. Canadian we don't have it here. QCell we have it here. In Cyberjaya we don't have Ryzen. We don't have CHNT. We have First Solar in Kulim High Tech. We don't have Suntech. So see, out of the 10, we have 5 in Malaysia. 5 out of 10 in Malaysia. Okay. So all the top guns, the top 3 are based in Malaysia as well. Okay. So we have quite a number of students from physics who are now working in Jinko and JA as well. So some of them started with their internship last time before they were absorbed as a permanent engineer in Jinko and JA. Right. So yeah, a couple of news on emerging technologies. So this is based on silicon solar cells. So if you look at the structure here, so let's look at the structure and try to relate with what you've learned last time. So this is based on heterojunction, okay, heterojunction technology. So this is manufactured by Kanika Corporation with 26.33 conversion efficiency based on crystalline silicon. And look at the heterojunction structure down here. So they use crystalline silicon as the light absorber. And then look at the front side. They have passivation layer on the front side. And then they have intrinsic morphous on the rear side. And then p-type morphous on the rear side. So the heterojunction is made between crystalline silicon to amorphous silicon in this case, intrinsic and p-type crystalline. So in this case, if you notice the p-n junction, the p and n contacts are made on the rear side, okay? Back contact technology, right? So this is a back contact technology. So we used to learn about front side contact and rear side contact. but this is only the basic form of a PN junction. It also can take this form, which is what we call IBC, interdigitated back contact. Interdigitated, let me spell interdigitated. BC is back contact, yeah, back contact. So that means all the contacts, positive and negative polarities, are placed at the back. So that means if you talk about carrier separation and carrier collection, you have to be, the carriers need to be separated at the rear junction instead of at the front junction. Okay, so usually this technology is based on N-type wafer, because N-type wafer has a higher quality in comparison to P-type wafer. So this is usually targeted for premium products where the conversion efficiency is very high. So rear junction technology, yeah? IBC, interdigitated technology. Right, another emerging technology is based on perovskite. Perovskite is a new technology. So it is a hybrid between organic and inorganic. Organic, it's a hybrid, yeah? Hybrid organic with inorganic. Inorganic. So it is based on MABX3 structure. So the typical form is called methyl ammonium. Ma here is methyl ammonium. Methyl ammonium stands for the Ma. Methyl ammonium lead. It is based on lead, unfortunately. So what is bad about lead? Lead triiodide. Anyone? What is bad about lead? Methyl ammonium lead triiodide, or this CH3NH3, which is methyl ammonium, lead PB, I3 is triiodide. So that is the perovskite structure that we currently using. So anything bad? What is bad about lead? What do you know? This device, this perovskite has lead. Is lead good or bad? Yeah, poisonous. Okay, lead is poisonous. Do we use lead in our daily life? Where do you use lead in our daily life? In your lab or maybe something? Where do you use lead? Anywhere? Any applications of lead that you know? It's toxic, yeah? It's very toxic if it's not controlled. So if you use lead in solar cells, if the lead leaches, leaking, battery ada lead tak? Lead tak? If the lead leaks into the environment, for example, because you eventually deploy the solar panels, solar cells out there to harvest the energy. So if the lead leaks into the environment, then it can go into the soil, into the water and everything, right? It's going to be dangerous. But unfortunately, the best technology of perovskite at the moment is based on lead. So it's called methyl ammonium lead triiodide. So if you look at the the curve there, the absorption coefficient against the wavelength. So we learned about this while comparing the absorption coefficient of crystalline silica, indium phosphide, cadmium telluride, gallium arsenide last time. And let's look at the absorption coefficient of this device. Okay, so look at silicon. Silicon is down here. So silicon is here. So if you look at 600 nanometer, so that's about 0.5 of 10 to the 7. On the other hand, if you look at perovskite based on lead, so it is somewhere 0.7, right? It's a lot higher in comparison to silicon. Okay, it's also comparable to cadmium telluride. So cadmium telluride is very high. So this perovskite is direct bandgap as well. Direct bandgap. So it's based on organic plus inorganic. So if you look at this compound, methyl ammonium lead triiodide. So which one is organic? Which side is organic? CH3, NH3, PbI3. Yang mana yang organic side? Did you learn about organic materials last time? What is organic material? What do you define as organic? Nanti ada presentation on organic solar cell ya. I would like to know more about what is organic. Anyone? What is organic? Right? CH3, NH3, right? Methyl ammonium. So the methyl ammonium, the Ma component here, the Ma component dalam ni. So you have MaBX3, right? But the Ma is organic. Ma is the organic side, if you like, right? Ma is organic. The BX3 is non-organic. So therefore, we call it as inorganic halide perovskite. So we call it halide because it's based on group 7, right? Group 7, iodide, chloride, bromide. So this triiodide, you can change with trichloride. You can also change with tribromide. Chloride, CHO, chloride, bromide. Okay, you can even tune the band gap of the perovskite by substituting this iodide to chloride. So that will change the band gap, increase the band gap. If you change chloride to bromide, that will even increase the band gap. So you can tune the band gap of perovskite. So one of the advantages of this perovskite is tunable band gap. Okay, you can tune the band gap according to the element that you put into the compound. For example, if you change from iodide to bromide, you will change the band gap accordingly. On the other hand, you can also replace the methyl ammonium with something else. Okay, it can also be cesium, rubidium, tin, germanium. Tin, germanium, you can alloy the different metals together in order to replace. You can also replace the lead component there with some other stuff like tin, for example. Okay, but the performance for lead-free perovskite at the moment is not as good as lead-based perovskite. So if you look at the solar cell based on perovskite, this is the structure, the device configuration that you can see on the left-hand side. Okay, the sun is coming from the top, and then we have a glass. So it's deposited on the glass because the perovskite layer is very thin. So the thickness is typically around 300 to 500 nanometer. It doesn't have to be very thick because the absorption coefficient is already high. Okay, so usually if you have a very high absorption coefficient, that means your absorber layer thickness, the perovskite thickness, doesn't have to be so thick because it absorbs effectively already, right? So beneath the glass, you have TCO as the contact, TCO or ITO. That the most famous one is ITO. And then we have electron conductive layer, typically based on TiO2. You can also use some other N-type based material like zinc oxide, TiO2, or some other layer. And then perovskite is in between, is sandwiched between your electron conductor and hole conductor. And the hole conductor is more P-type, like nickel oxide, like spiral or metat. You can search on these later on, spiral or metat. We never learned about this. It can also be organic material like P dot, PSS, a hole conductor, and then followed by an electrode at the back. So this electrode can be silver, can also be gold. These are the most common ones. Okay. Oops. So yeah, so this is how the perovskite looks like. If you hold it, it can also be deposited on plastic substrate, plastic. So today, if you look at the world record chart that I shared with you in the last class, the perovskite conversion efficiency has now reached about 25%. 25% with a single junction. Right. The goal here is to incorporate perovskite on top of silicon. Okay, say you have a good silicon solar cell, that will be a one junction, one PN junction based on silicon. Then you will deposit another layer of perovskite solar cell. So then you're going to have two pairs of PN junction that's based on perovskite, on PN junction that's based on silicon. So in this case, you're going to have two solar cells stacked together. So the perovskite will be the top cell, and the silicon will be the bottom cell. So when the light is coming from top, perovskite will be harvesting all the short wavelength and the visible region photons, and the silicon down here will be absorbing the IR photons, okay, near infrared onwards. So in this case, you can have wider spectrum being absorbed by the solar cell, delivering higher performance. So that's why you can see on the right here, perovskite that is stacked on silicon. Perovskite stacked on silicon, double junction, okay, double junction, 2PN junction. So a bit of news on perovskite. This is 2019. So single junction perovskite based solar cell with up to 24.23% conversion efficiency, right? This is by Crick, K-R-I-C-T. Crick is the famous institute for perovskite. So Korea Institute, Korea Research Institute of Chemical Technology, right? It's based on perovskite. So this is another news in 2018. This is by Oxford PV. Oxford PV is a spin-off company from Oxford University. So this 28% is based on double junction. Okay, double junction. That means perovskite on silicon. Perov on silicon. So it's a two junction. PN, PN, yeah? PN, PN. Two PN junction. Two junction. Or we call this as tandem. Tandem technology, which means two junction. Tandem means two. Okay. So perovskite on silicon. So the conversion efficiency is 28%. So remember last time when we talk about Shockley-Queisser limit of silicon, SQ limit. So I told you that the theoretical efficiency of silicon is about 29%. So that is the maximum that the silicon can deliver. So beyond 29%, there's no way silicon can deliver alone. So the goal of incorporating two cell perovskite on silicon is to go beyond 30% conversion efficiency. That will not be possible with silicon alone. So at this moment, in this case, perovskite Oxford PV has achieved 28%, not yet exceeding the 30% ceiling for the conversion. Okay. So this is now the news. I think last year, 29.15 by Hemo Zentrum in Berlin, East Zagby, Berlin. So perovskite on silicon as well, tandem cell. Last year, okay. So everyone is trying to break the 30% limit. It's still striving to do that, but it's not that easy. So to be able to do that, you need to have a very high performance silicon cell coupled with a very high performance of perovskite cell. So another emerging tech is called black silicon. So you can see here that the surface of the wafer looks black. Okay, so you can see this wafer on the left. This is multi or mono wafers. Multi or mono wafer. This one. Look at the wafer there. Multi or mono? Multi, right? So you can see all the grains there. So it's multi-wafer. But the black silicon is produced in the center. BSI is black silicon. So you can see the central region is black due to the presence of black silicon. And the outer edge is the original multicrystalline that is very reflective. So if you look into the black So it is black because the region in the center is occupied with nano textures. So nano textures like this, you can see the cross section of the wafer. So the scale bar here is about 200 nanometers. So that means this height is only around 700 perhaps nanometer. And the width of the nano textures is about 200 or so, 200 nanometer. So some is even less than that, 100 maybe. But essentially they are all nanostructures. Okay, all nanostructures. When they are nanostructures, there will not be any, the light will not be scattered. There will no scattering of light on the surface of the wafer. On the other hand, the light will be coupled into the silicon. So if you look at the standard silicon wafer, that typically reflects around 40% of the incident light, just like what I showed you to you just now. You have an incident light of 100%, but 40% is lost if you have a flat surface. So this is the 40% that is lost to the environment. And if you incorporate micro scale pyramids, the conventional technology, micro scale pyramids, which is typically about 8 micron wide and 5 micron height, so 5 to 8 micron in dimension, that will give you a lower reflection, but it's not as low as compared to the black silicon. If you see here, the black silicon, the reflection level is about 1% or so, but the pyramid here, the blue one, is a bit higher. Okay, it's a bit higher. So since so less light is reflected back to the atmosphere, and most of the incident light is coupled into the silicon for light absorption, the surface appears black. So you see black because barely any light is reflected. Okay, so if you look at this technology, a couple of years ago, Trina Solar has converted about 23.5% of the light into electricity. So that'll give you 23.5% of conversion efficiency for Trina Solar based on black silicon multi-crystalline wafer. Okay. So if you look at this, the left-hand side is the black silicon. So the left-hand side is a black silicon. This is by Suntech, another company from China. And the one on the right is pyramid plus ARC. If you look at the pyramid plus ARC, let me just draw to you. If you look at the reflection curve, you want to reduce the reflection to as much as possible. If you look at the reflection curve within 300 to 1000 nanometer, the pyramid with ARC will probably give you something like this. Okay, the reflection curve. Okay, case number 1 is black silicon, case number 2 is pyramids. So this is probably case number 2, that you're gonna get some kind of reflection curve like that. So this probably about 2 or 3%, say about 2%. So this is probably around 15%. So if you use black silicon, it's going to suppress the light reflection to this level. So it's going to go really low. This dashed line is the black silicon reflection. So this case number 1. Okay, so that's why it appears black. So this one, the left-hand side is based on nano textures, nanoscale textures. The right-hand side is based on microscale textures. The nanoscale, kecil. So nano textures less than 1 micron, and the right-hand side is based on microscale textures. Right, so that's how they look like to our naked eyes, black and blue. So the blue one is the typical one that you see on the roof. Okay, the standard solar cell is based on case number 2. So yeah, this is what I drew just now. You can see the pyramids. This is the case with pyramids. alone, if you don't have any nitride, so these pyramids without ARC, so you're going to get reflection curve like that. And on the other hand, if you use black silicon, you're going to get something like that. So that's about 1% of reflection. So micro scale on the left, conventional one, and black silicon and textiles on the right. Okay, so case number one, usually about 10% reflection. So that's about 10% more or less. So this is about 1% on the right. Okay, black silicon is about 1% reflection. That makes it black. So we also have some work going on in our group. This is one of our first publication 2 years ago. That was 2019 in my team last time. So we did fabricate black silicon as well, using a process that we call silver assisted chemical etching. If you're interested, you can go to this paper, or you can ask from me later on. This, you can see here, this is the planar silicon. If you don't do anything to the silicon, planar crystalline silicon, the one with 40% of light reflection. So these are all our black silicon. Okay, so at the moment we can reach down to around 3% of light reflection. 3%. So that means if you reflect, if plot reflection curve, our curve looks like that. Then this is about 3%. And the conventional thing, the planar is like this, 40%. Okay, this is based on our no labs work from my MSc student last time. So here, at the moment, we have more and more works, more and more publication. The recent one in 2020 and 2021 as well, based on black silicon from various processes and various approaches as well. Different type of catalysts. So in this case, we use silver. You can also use aluminium. You can also use nickel, palladium, platinum, copper, gold, many more catalysts. But in this case, we use silver. And our recent process uses aluminium, which is the first process in the world that uses aluminium. So this is just published early this year. Okay, so 2021. You can check it out. A paper by my team on Google. So the first work published by my PhD student from India. So this is only the first publication back in 2019. You can look for more publications on black silicon from our team. So we also have another technology in the market that's based on amorphous silicon. I think some of you are going to present on amorphous silicon as well. So amorphous silicon is not crystalline silicon. We learned about that. And it has a band gap of about 1.8 electron volts. So it's based on amorphous materials without any crystalline arrangement. Okay, without any crystalline arrangement. And this is how the band gap of crystalline silicon looks like. And then we have trap states in the band gap due to the presence of defects or dangling bonds. Okay, dangling bonds. Dangling bonds to bonds that are not terminated well. Okay, dangling bonds on the surface that will reduce the performance of the solar cell upon illumination of the light first time. Okay, so the performance will be reduced due to Stabler-Wronski effect. Stabler-Wronski. We call it SW effect. SW effect. Stabler-Wronski effect. Try to look into this. We're going to have a presentation on that, right? So any group working on amorphous silicon for your presentation? Ada kan? Betul ke? Ada kan? Any team working on amorphous? I couldn't recall the list. Any groups working on amorphous silicon? No? Tak ada? No. Ada ke? Tak ada? Okay, no, right. Okay. I'll give you more references on the amorphous silicon then. I thought one group is covering this. Okay, it degrades due to Stabler-Wronski effect. So the performance will be reduced first time upon exposure. Kemudian dia akan they can stabilize and then it will go back up and then stable. Okay. So morpho silicon ni kita pakai dekat calculator, dekat low power devices, calculators, watches, and low power devices. Maybe some sensors. We hardly use this one for rooftop or for solar farm because the conversion efficiency is not that high. Okay, and then it doesn't last as long as crystalline silicon. Right, another technology, this one of the groups will be presenting, cadmium telluride, is based on technology that's manufactured by First Solar that we have in Kulim High Tech Park. So the absorber layer in this case that does the light absorption is cadmium telluride. So the band gap is somewhere 1.5 electron volt. Cadmium telluride, okay. So cadmium telluride is p-type, and then we have cadmium sulfide that is n-type. So that will form the junction, and then the light comes in from this way. You can also flip the cell. It doesn't necessarily have to be this way. You can just flip the cell and cadmium sulfide will be on top, followed by cadmium telluride, followed by back contact based on this alloy, right? And then the silver contact eventually. So the overall thickness is somewhere around, I think the cadmium telluride thickness is about 2 micron, and the whole device thickness is less than 5 micron. Okay, so I'm just going to see the presentation later on. So this is an example of panel produced by cadmium telluride. So the recent one is called S6, more than 400 watt per plate, right? So this plate gives us more than 400 watt. So the size is quite big, and it will be handled by automation in the fab because it's too big, right? It's too big, and therefore it's quite heavy. So can anyone guess what's the typical weight of a solar panel? Anyone can guess typical weight? Any guess? Berapa berat satu panel kalau you nak angkat? So kalau you nak kerja in the solar factory, you have to be able to lift the panel as well sometimes. Not all the time, because most of the times it will be handled by the automation, but sometimes you may need to. Guess what's the weight? Anyone? 1 kilo, 1 kilo only. The conventional one. Well, if you talk about the small size, yes, 1 kilo. If you talk about the standard one, the one that you see on the roof or in the solar farm, yeah, the Arena 20 kilos, Calvina 16, Faris 15, 20. Okay, any other? Alia 20, right? Adali? Any other guess? So most of you somewhere 20, all right. So it's about 20 plus, okay? It's about 20 plus per plate. And kalau you angkat satu tu, that's about 25 or so kilos, depending on the technology and the plate size, okay? The module size, but somewhere 20 plus kilos. If you go for the latest panels are bigger in size because they use bigger wafers, but use the same number of cells in the panel, but that will end up into a bigger panel. Okay, so that's about 25 kilos on average, but the bigger ones will be a lot heavier then, right? So satu plate tu kalau you boleh angkat 25 kilos or so, then it should be okay. All right, and then another type is called CIGS, copper indium. This one is second generation, copper indium gallium selenide. CIGS 6, we call it 6. So the whole device thickness is usually about 2 micron or 3 micron, just like the thickness of cadmium telluride. And it can even be deposited on a foil, on a plastic foil that's bendable. So therefore you can use this one on any surfaces. It's not rigid like the glass-based panel that's rigid in in structure, so therefore it's not so flexible. So this one is very flexible. Okay, you can do on plastic, you can do on fabric, you can do on glass as well if you want to. Okay, so if you look at this, p-type is based on the CIGS is p-type, cadmium sulfide is used as n-type, so that will form the junction. So it is a heterojunction. Okay, heterojunction. TCO is used as a contact, typically ITO, and then you have molybdenum back contact. Metal, molybdenum, molybdenum, right? So you have also have glass, plastic, you have some other substrate at the back. So this is another technology based on CIGS. So another technology is based on cadmium, zinc, no, copper, not cadmium, copper, zinc, tin, also alloy, sulfide, ZAT386. It is abundant on Earth, in Earth. So it's more abundant than CIGS because CIGS has indium. Indium is not in big supply, right? So you're going to have a lot of indium supply issue if you have to fabricate or manufacture big volume of the solar cells based on indium. So on the other hand, ZAT386 is abundant in nature, abundant technology. So the whole device thickness is less than 3 micron as well. So the light absorber is the ZAT386 layer, the p-type, and then the n-type is cad sulfide, makes the heterojunction, and you may also include intrinsic zinc oxide, TCO, and molybdenum contact as well on glass in order to hold the device. Okay, so the light is usually coming from the front side. So this is how it looks like. This is from UNSW. ZAT386. So the current efficiency is only around 10%. It's so low if you talk about mass production. CIGS, I think somewhere 15% or so. Okay, about 15%. So the recent one is called perovskite. So perovskite, yeah, this is one of the latest technology being manufactured. So this is the technology in Poland by this CTO, Dr. Olga. Right? So this is how the perovskite looks like. Perovskite cell on glass, perovskite on plastic, perovskite on plastic. Okay, in Poland. Okay, in Poland. So these are the companies. Sol Technology. You can see the news here. Just 2 weeks ago, they announced the opening of a mass production line. Okay, fabricating perovskite. So this one is like big size on plastic. So this is another news. Also about 2 weeks ago. So they just launched a production line. So before that, it was like a few years, 2-3 years. They ran some pilot line on perovskite based on inkjet printer. So I forgot to mention that it's based on inkjet printing. So just like the way you print your paper using inkjet printer, but instead of printing the paper using cartridge on the paper, but we use perovskite ink to print on plastic. Okay, to print on plastic. The concept is similar to our printing, our day-to-day printing. It's very cheap, very simple, very fast. But it can do large scale as well. So another technology from 3rd gen is called OPV or organic PV. We're going to have one group presenting on organic PV. So O there is organic. So we're going to see more in the presentation later on. So we have polymer active layer to do the light absorption. We have electron transport layer N-type. We have hole transport layer P-type to sandwich, untuk kepit lah, to sandwich the polymer layer that will do the light absorption. And this is more towards carrier extraction. And you have metal cathode and then ITO on the front side, and the light is coming from the front. And it doesn't necessarily have to be drawn from this side. You can also flip the configuration to show that light is coming from the front, and your ITO and the substrate is going to be on the front side, and the metal cathode will be on the rear side. Okay, So it can be done by printing process. This is just like this is called roll to roll printing. Roll to roll, R to R, roll to roll. It's a very fast process, scalable, and low cost as well. Some book references if you want to read. So couple of good books here. The first one I read in 2008 was this book. This was the first one I read to know about solar cell when I learned from zero. And a couple of good books from UNSW, from Professor Martin Green, Professor Stuart Wenham, Professor Martin Green. These are all good books on solar cells, right? If you want to explore. So yeah, that's done for solar cell. I want you to try this out. Look at this question. You can try for yourself. The question asks you to calculate the VOC. Remember last time we talked about the IV curve of solar cell. This is the JSC, this is the VOC, and you are required to calculate the VOC. And you are given with a few parameters. The doping level, you need to draw this first in order to understand. Where's your N, where's your P? NA is given, ND is given, diffusivity for both, lifetime for both, and then the GL, the photocurrent in the solar cells is also given. And then from there you can use these parameters to derive your short circuit current, your saturation current density. So this one will be your saturation current density, or equals to J naught also. Okay, given by that equation, you can convert into this, and then you will find that in this equation, everything is known except the Ln and Lp, which you can calculate here from d tau square root. Okay, d and tau are given, and you can get the diffusion length for electron and for hole. Then the moment you know this, you can go back to this original equation and calculate the saturation current density, J naught, right? So the moment you know the J naught, we learned last time that VOC is reciprocal to J naught by an equation. And you can see here, so the J naught here is the here and here, reciprocal, right, to VOC. So you can plug in into this equation, VT ln 1 plus JL over JS. JL is given, VT is known because you know the temperature, KT over Q. JS just calculated here, just calculate JS, and you can plug in everything to get VOC of 0.514. So that means here will be 0.14 volts. Okay, try for yourself. Everything is given already. You just have to know which equation to use. But you have to use, you have to go through a couple of derivations first before you can get to the answer. Okay. Yes, we're done with solar cells. Try the calculation for yourself. Yeah. So any question on solar cell? You're gonna see more on solar cells from the presentations later on. Any questions so far on solar cells? Okay, all good. You can understand the content so far? I don't have time to really go into every single technology in detail because they all take longer time. Okay. So any questions, guys? Is everything okay? All good then. No response means good. No news means good news, right? So anything for tomorrow? Anything for your presentation? Any last question? If you're not sure of anything on the presentation? Nope. All prepared? Everyone prepared? Yes, you have to turn on your camera. Turn on your camera, be visible on the screen. I would like to see your faces. Oh, you don't have the camera? If you don't have the camera, then no choice. If you have the camera, turn on the camera. I want it to be visible on the screen during the presentation. So say you have 5 of you. So I want the 5 of you to be visible on the screen during the presentation. Okay. So remember, everyone has to present in turn, and you are given 20 minutes to do the presentation, and we're going to have Q&A from your friends, from your colleagues, and then from me as well. So they'll take about 30 minutes max, and then we're going to proceed to the second group and do the very same thing. So we're going to have 2 groups per session. So tomorrow will be for group 1 and 2. And then the next day will be 3 and 4. Okay? So any other question on the presentation? Nope. All good. Okay, then I'll see you tomorrow. All the best for your presentation. Bye-bye. Assalamu alaikum. Take care.